Okay, so in the corner of a piece of graph paper, I want you to just kind of turn it 45 degrees, and I want you to write in the corner A, B, C, D, E, F, G, H, I, and J. And what I want you to do is you're going to start at point A, and you're going to walk to any of these other points. So to get from, so for example, to get from like A to I, you might go A, C, F, I, or A, B, D, H, E, I. Now, so there's many ways to get from A to I. I want you to find the shortest way to get from A to any point, and then I want to know how many ways you can do that. So for example, obviously, A to B, it's the shortest route from A to B, and there's one, so it's the shortest route. And there's only one way. Now, AB, AC is the same thing. Let's look at AE, though. So you can say to me, you can say, okay, there's A, B, E. That's the shortest route from A to E. Once again, there's other ways. So let's see, there's A to B is 1, B to E is 2. There's 2 steps. Is there another way to get from A to E in 2 steps? And you say, yeah, go to A to C, and then C to E. That's also 2 steps. So you'd say there's 2 ways to make the shortest route. So I'm going to you to put the number 2 here. And I want you to figure out for all these numbers, I want you to figure out the shortest way to get from A to the point, and then I want to know how many other ways there is to go to that shortest route. You can actually, J, you can put K, let's see, L, M, N, and O. Now, good luck. Okay, we're going to be doing binomial expansion. And so I asked you to, in the video, I asked you to do that grid thing. It turns out that the numbers were Pascal's triangle, something called Pascal's triangle. So if you notice, they end up being like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. You'll notice a couple of things about the pattern. You'll notice that a row, an entry is the sum of the 2 above it. Also, you might notice that if you add the rows across, they're all powers of 2. 1, 2, 4, 8, 16. I can do the next row. 1, 5, 10, 10, 5, 1. So the question is, what are the connections with what are the connections here? So, well, the first thing is let's make a connection. Can you see that? Yeah. Let's make a connection back to chapter 1. Chapter 1, and that was a n choose k, right? This is n choose k. This is n. Remember, it was n factorial over k factorial times n minus k factorial. But I want to take a different look. I want to look at 0, 0, 1, 0, 1, 1, 2, 0, 2, 1, 2, 2. And so the idea is we can do 3, 0, 3, 1, 3, 2, and 3, 3. So let me ask you something. How many ways are there to do nothing? So the answer is 1. Right? Here's 1. If you have one object, so remember, we're choosing, right? N choose k. So I have one object. How many ways are there for me to choose none of them? You say, well, 1. How many ways are there for me to choose 1 from one object? 1 again. Now let's go to the third row, right here. 2, choose 0. How many ways are there for me to choose? From 2, I have 2 objects. How many ways are there for me to choose none of them? You go, oh, 1 way. Now you have the 2 objects. How many ways are there for you to choose one of them? Well, I could choose the first or the second. I have 2 objects. How many ways can I choose both of them? Well, there's 1 way. And we see there seems to be a connection. So let's do the last row together. You have 3 objects. How many ways are there for me to choose none of them? 1. I have 3 objects. How many ways are there for me to choose one of them? Well, I can choose A, or I can choose B, or I can choose C. I have 3 objects. How many ways are there for me to choose 2 of them? I can choose AB, I can choose AC, and I can choose BC. Last, I have 3 objects, ABC. How many ways can I choose all of them? Once. Remember, it's choosing, combination, order doesn't matter. And we see once again that this first problem with the pathways kind of connects this idea of combinations, combinatorics. And actually, you can figure out any of these things by just expanding the chart. So you can kind of be like, you know what? 1, 4, 6, 4, 1. 4, choose 0. 4, choose 1. 4, choose 2. 4, choose 3. And 4, choose 4. And so, can you see that? Oh, you know what? Let me make it darker. So, if you wanted to quickly figure out how to do combinations of like 4 choose, you just go along the chart. So let's see. Let me erase this. Sorry. So we can do 4 choose 0 is 1. 4 choose 1 is 1 plus 3 is 4. We can do 4 choose 2, which is 6. We can do 4 choose 3, which is 4. And we can do 4 choose 4 is 1. While we're here with Pascal's triangle, here's an advanced exercise. What we seem to notice is that, for example, so here's an advanced exercise. What we see in Pascal's triangle, whether the entries are the pathways in a grid or the solutions to combinations, we notice that this pattern, 1 plus 2 is 3, or 3 plus 3 is 6, 6 plus 4 is 10. It works. So let's say this is row n, right? So we have n, right? Choose 0, right? So and choose k. We go over another plus n choose k plus 1, and that takes us down to, let's see, so let's think about this. If this is row 3, entry 2, this is row 3, entry 3, then when we add together, we get row 5, entry 3. And that's nothing to prove. Send me an email, let me know if you got that. But let's move on. So the question is, how are we going to connect this to binomial expansion? What is the idea behind binomial expansion? The idea is expanding a binomial. So for example, you're going to be asked to expand, I don't know, here's something, 7x plus 5 to the 4th power. Okay? And they're going to say to you, find the x to the 3rd term. So the first thing we need to talk about is exactly, is there a fast way to expand this out? Well, let's expand this out. So the first thing is, I want you to see that the expansion has a connection to the binomial, to the Pascal's triangle. So I'm going to ask you to start with something simpler. First of all, what's x plus 1 to the 0? 1. What's x plus 1 to the first power? X plus 1. X plus 1 squared. Well, let's take it off to the side. So we have, I'm going to tell you to use the box method. X plus 1, x plus 1, x squared, x, 1. So we have x squared plus 2x plus 1. How about we take a look at x plus 1 to the third power? Well, I'm going to have x squared plus add 2x plus 1. And I have x plus 1. X cubed, 3x, 2x, x, 1, 2x. I apologize, this is 2x squared, this is x squared. Final answer, x cubed plus 3x squared plus 3x squared plus 1. Let's do the last row. Now we're going to do x to the third plus 3x squared plus 3x plus 1. And then we're going to do x plus 1. Let's see. X to the fourth, 3x cubed, 3x squared, x, 1, 3x squared, x cubed. Let's add all these terms together. So we get x plus 1 to the fourth is equal to, let's see, x to the fourth plus 4x cubed plus 6x squared plus 4x plus 1. Well, why am I making you do this? The first thing is, what you should notice is that all the coefficients, well, first of all, one thing, if we raise something to the 0 power, there's one term. If we raise something to the first power, a binomial to the first power, we have 2 terms. If we, for example, if we raise something to the 4th power, we have 5 terms. So first thing you notice is that a plus b to the n has n plus 1 terms. Right? That's something we need to know. There's n plus 1 terms. Okay? Next, the next thing I want you to notice is that if I put all the coefficients in here, if I put all the coefficients here, you start to notice something. You notice that the coefficients on the expansion correspond to Pascal's triangle. So there's that connection. Let's expand that. Let's expand this out. Let's continue. So I look at this problem. I'm not really sure what's going on here. I want you to figure this out. I would like you to do this next thing once and only once. What I want you to do is expand 7x plus 5 to the 4th power. I want you to do that by hand. So this is the one thing we're going to do this by hand. I'm going to skip jump the video, so the answer is going to be right here when we're done. Or, you know what, I'm going to do it right now on the board. Well, we're going to skip jump it. So I multiplied 7x plus 5 times 7x plus 5, and then I multiplied it again to get this whole big thing. Bear with me. Actually, I made a mistake here. This is x to the 4th. Okay, bear with me. So we have this really long polynomial. It's a mess. I mean, surely I'm not going to make you do this over and over again. So we have 49 x squared x to the 4th plus 70 plus 49. Well, 70 plus 49, 70 plus 49. So you know what I'm going to write that as? 249 times 70 x squared to the 3rd, sorry. X to the 3rd. Good. Okay, what's going on with the x squares? Well, I have 2549, 2549, so that's plus, let's see, that's 50, 49, plus 70 squared, x squared. Okay, just take care of that. What's going on here? Well, this is 50, 70. And then the last one is 25 squared. Bear with me. I'm going to move. Good. So what I'm going to ask you to do is factor out of the 5s, the 7s, and the x's. And whatever's remaining, we're just going to combine that together. Okay. What's going on here? Well, I have 7 to the 4th, x to the 4th. What do I have here? What do I have here? Well, let's see. 40, so I have 2, 7, 7, 7, 2, 5, x to the 3rd. What's going on here? Well, I'm going to factor out, let's see, I can factor out a 7, and I can factor, so let's, ready? Let's see, 40 times 49 plus 70 squared. I'm going to pull out a 10, and I'm going to pull out a 7. So I have 5, 7 plus 70. Then I'm going to pull out another 7. And then I'm going to pull out another 5. What's going on over here? 50, 70. This part, I'm going to pull out a 10. Oh no, I'm going to pull out 100. And I'm good. So I have 5 squared times 4 times 5 times 7, and this is 5 to the 4th. Okay, let's clean this up once. I'm not asking you to do this. I'm just making a point. So let's clean this up. Let's see what we got here. What do we got here? What's going on? Well, this is 7. So the first term is 7x to the 4th plus, what's going on here? I have 7 to the 3rd. So I have, let's see, I have 7x to the 3rd times 5 to the 1st. What's left over? 2, 4. What's going on in the next term? Let's see. Well, some of you might say, hey, Mr. Adler, that 7x went from a 4, now it's a 3. Maybe it's 7 squared x squared. Well, you'd be right. 7 squared here. And then, yeah, and then the x squared, you're correct. Now, you're also saying, hey, Mr. Adler, there was no 5 here, there's 1 5 here, now there should be 2 5s. 1, nice, this is 2 and 5, nice. And what's left over? Let's see, 3 times 2, that's my 6, nice. Let's continue. Hey, Mr. Adler, 7x to the 4th, 7x to the 3rd, 7x squared, 7x. Nice. There's 1 7. It's 5 to the 0, 5 to the 1st, 5 to the 2nd, 5 to the 3rd. Nice. 5 squared and 5. What's left over though? I got rid of the 5 squared, I got rid of the 5. What's that? The 4. Last but not least, 7x to the 4th, 7x to the 3rd, 7x squared, 7x to the 1st. There should be no 7x, which there isn't. 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3, 5 to the 4th. And you'll notice that the coefficients are from Pascal's triangle. So once again, I'm never going to make you do this. I'm never going to make you do that again. But the idea is, what's the formula? What is the formula for x plus a to the n? And that's equal to the summation starting from 0 up to n of n choose k, a to the n minus k, b to the k. And so the idea is, when you're expanding a binomial, the first combination, so k starts at 0, and so you have n minus 0. So a gets the highest power, and then b gets the 0, and then each time k goes up, counters up, the exponent starts to drop, but the exponent for a starts to drop, but the exponent for b starts to go up. Now, you don't have to memorize this, because that's not how I teach the kids. The way I did it old school was like this. So let's take an example. 2x plus 3 to the 4th power. How did I, well, let's start with something, I'm sorry. Example 1, old school. Example 1, Adler, old school. Example 1, x to the 3rd to the 4th power. So what I would tell the kids to do is, I would say, okay, first of all, draw Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. I know that if I'm raising them to the 4th power, there's going to be 5 terms. Next, I know I have x to the 4th, 3 to the 0. X to the 3rd, 3 to the 1. X squared, 3 squared. X to the 1st, 3 to the 3. X to the 0, 3 to the 4th. Put on Pascal's triangle. 1, 4, 6, 4, 1, and you're done. Clean it up. X to the 4th plus 12x cubed plus 54x squared plus 108. What's 27 times 4? Yeah, 108x plus 81. And that's how you expand a binomial out. Let's do 1 or 2 more examples. Old school Adler way. So the idea is, get down Pascal's triangle. You know the coefficients go down. The a's go down as the b's go up. Keep in mind, so let's do another example. 2 more examples. 2 more examples. And then we'll move on a little bit. Next example. 2x plus 3 to the 5th power. Same idea. Get Pascal's triangle down. You know what? The problem's there. Do the next row. 1, 5, 10, 10, 5, 1. Knock this out. Now first, so let's see. We have 1 times 2x to the 5th, 3 to the 0. Next, 5 times 2x to the 4th, 3 to the 1, plus 10 times 2x to the 3rd, 3 squared, plus 10 times 2x squared, 3 to the 3rd, plus 5 times 2x to the 1, 3 to the 4th, plus 1 times 2x to the 0, 3 to the 5th. That's how you expand these out. Now, they don't ask this anymore, so they get a little more tricky, but as long as you know how to knock these out, old school, you can get the answer. So let's clean this up. What do we have here? 32x to the 5th plus 80x to the 4th, because 16, I'm sorry, no. We have 2 to the 4th is 16. 16 times 5 is 80. 80 times 3 is 240. What do we have here? 8 times 9 is 72. 72 times 10 is 720, x to the 3rd, plus 9 times 4 is 36. 36 times 10 is 360x, plus 81 times 2. Well, let's see. 81 times 10 is 810. X plus 3 to the 5th, 243. Next, pay attention to negative numbers. Let's keep the next one simple. X minus 5 to the 3rd. Let's keep it very simple. X minus 5 to the 3rd. Pay attention to your negatives. So once again, just visually, we know 3, you can do this over and over again. 1, 1, 2, 1, 1, 2, 1, 1, 3, 3, 1. These are my coefficients when I'm raising a binomial to the 3rd power. So what do I have? 1, x to the 3rd, negative 5 to the 0. Next, 3, x squared, negative 5 to the 1st. So we're fluctuating, positive, negative, positive, negative. This is, if you think about it, this comes back to the series and sequences unit that we just finished. When there's fluctuating terms in the sequence, this is where that comes from. What's going on next term? 3 times x to the 1st, negative 5 squared, and then 1 times x to the 0, negative 5 to the 3rd. Final answer, what do we have here? We have x to the 3rd minus 15x squared plus 75x minus 125. This is where the fluctuations come in when you start introducing negative numbers. Now, there's no reason why I can't ask something like this. X plus 2 over x to the 5th. So you say, well, that's weird. No, it's the same idea. This is A, this is B. It goes in. Now, let's hold off on this for a second. Well, let's hold off on this for a second. Because, once again, this is a binomial. This is something times something plus something raised to a power. Okay? Before we move on, any observations you noticed about this? Well, the next observation I noticed is that the sum of the exponents, what's 3 plus 1? 4. Not a coincidence. What's 2 plus 2? 4. What is 3 plus 1? 4. What's 4 plus 0? 4. We see it over here also. I raised it to the 4th power, so the sum for 4, 4, 4. What's going on up here? Well, I raise it. This is the 5th power, and it seems like the sum of the exponents is 4, right? 5 plus 0, 4 plus 1, 3 plus 2, 2 plus 3, 1 plus 4, 0 plus 5. The other thing I seem to notice is that, this is kind of cool also, this combination of 4 choose 0, this 0 always seems to connect to that 0. This is 4 choose 1, that 1 connects to that 1. If you choose any of these, for example, this is 5 choose 2. Well, that 2 connects to that 2. Over here, this 5 was 5 choose 4, which connects with that 4. Okay? Hold on to those two things. Because now I'm going to ask you a different question. I'm going to ask you something that you're going to say, Mr. Allen, that's too much. We can't do that. It's a lot of work. No. The next question I'm going to ask you is, what is the x to the 5th term of x plus 3 to the 8th? Because that's going to show up on an IB exam. That's a higher level question. So you say, well, I can't do a lot. That's a lot of work. Are you going to do Pascal's triangle to the 9th row? Are you going to write it in 9 terms? Old school, I used to make the kids do that, but I'm not doing that anymore. So what's going on? What does the x to the 5th term look like? Well, first of all, what does any term of an expansion look like? Well, we know it's something choose something, x to the something, 3 to the something. Okay? Well, I know that 8 goes up here. Right? What am I looking for? I'm looking for the x to the 5th term, which means that goes up here. Well, we find out what's the relationship between the exponents. We must say, Mr. Adler, they add up to 8, which means that's a 3. And I pointed out something. I said that 3 goes here. 8 choose 3, x to the 5th, 3 to the 3rd. It's obviously a calculator problem, but you still have to know how to set this up. This is your method. This is one part of the answer. What is 8 choose 3? Well, it's 8 factorial times 7 times 6 times 5 times 6 factorial over, remember, it's 3 factorial times 6 factorial. No. Sorry. Remember, it's n factorial over k factorial times n minus k factorial. So it's 8 factorial over 3 factorial over times 5 factorial. So we have 8 times 7 times 6 times 5 factorial over 3 times 2 times 1 times 5 factorial. This goes out with that. This goes out with that. We're left at 56. Final answer, 56 times 27, x to the 5th. Hey Siri, what is 56 times 27?
56 times 27 is 1,512.
Let's try another one. What is the x to the 3rd term of, 5x minus 2 to the 6th power? I know there's an x to the 3rd term in there somewhere. I don't know what it is. I don't feel like raising it to the 6th power, and although I don't feel like doing Pascal's triangle to the 7th row. You could expand it out, but this is only like a 4-point question. This is a 4-point question. You don't have that much time. What am I going to do? Okay, well I know every term is something choose something, 5x to the something, negative 2 to the something. This is just driving you crazy, those negatives, but whatever, that's IB. Okay, well, I know it's to the 6th power, and I know that 5x I want to raise to the 3rd power. Therefore, what is the power of -2? We know it's 3, and we know that ends up in here. So we're done. Figure this out. Let's see, 6 factorial over 3 factorial times 3 factorial. We have 6 times 5 times 4 times 3 factorial over 3 factorial, 3 factorial. That goes out with that. This goes out with this. So we have 20 times 120. So what do we have here? This is a huge mess, but it's not that bad. It's just a calculator problem. And obviously this will be on a part 2 question because the multiplication is not a 12th grade standard, excuse me. So we have 20 times 125 times -8. Don't forget that negative. I can't give you credit for it if you miss a negative. Sorry. 125 times 4, 125 times 4 is 500, so 125 times 8 is 1,000, -1,000, -20,000. X to the 3rd. Last problem we have to go. How are we doing for time? 34 minutes. It's a pretty long video. But this is the whole unit. The last problem we need to think about is what is the constant term for x plus 2 over x to the 8th? How are we going to figure that one out? Well, what does it mean? A constant term, it's like 7. And we know that every single one of these expansions has a constant term at the end. The last, like this would be like -2 to the 6th, or like this one would be like 3 to the 8th. And if you go over all your examples, you know that all these expansions have constant terms, but you're not really sure about that one. And you can kind of run it through your head. You can be like, okay, well I know it's like x to the 8th, 2 over x to the 0, x to the 7th, 2 to x over 1st. The question is there going to be a point where the x in the numerator cancels out the x's in the denominator? And you might say in your head, okay, you know what, it's 4 over 4. That might work. Be aware that there might be problems with higher exponents, but let's get the structure of how to find the constants. So, what's the constant term for x plus 2 over x to the 8th? You say, fine. We know that we have 8 over something, x to the something, 2 over x to the something. The structure is the same. But in this case, I don't know what to rate. I don't know what term this is. Well, math is math. In math, if you don't know something, call it B. Well, if I x raise x to the b, what is 2 over x raised to? Nice, 8 minus b. Remember, the sum equals 8. Okay. Now, let's combine these two terms together. So, I know I have x to the b times 2 to the 8 minus b over x to the 8 minus b. Okay, well, whenever I divide powers with the same base, I subtract the exponents. So, I have 2 to the 8 minus b times x to the b minus 8 minus b. Good. Let's continue it. So, and once again, and this goes in here. So I have 8, choose 8 minus b. I have 2 to the 8 minus b minus 8. no, 8 minus b, sorry. And then I have this term here. Well, these problems work out nicely. What is b minus 8 minus negative b? This ends up being 2b minus 8. Well, we're almost done. What did we say we were looking for? Well, we were looking for the constant. Well, what's not in the constant term? X. So let 2b minus b equals 0. B equals 4. Therefore, 8 choose 4, 2 to the 4th, x to the 4th, is the constant term. This became 0. This is 2 to the 4th. This is 8 choose 4. We're done. And that's how you find the constant terms. Obviously, you can fool around with these. Maybe I can put like an x squared, an x over an x squared, something like that. But it's the same idea. I need x to be raised to the 0 power. I'm going to stop the video, and you're going to work on the problems.